So we are live. Welcome to today's session of the Discrete Maths 2 course. What we're going to do today is to continue our discussion of a very important, basic but very important probability distribution, namely the binomial distribution that we started looking at last Thursday. And after having done that, we'll examine a couple of interesting probability-related puzzles, the so-called birthday paradox, and we'll also see how that is not so as odd as it might seem, because it relates to something that you're perhaps looking at. In fact, I'm sure you're looking at it, or you've been looking at it in the data structures course, namely hash tables. Having done that, we'll start our final topic in the course, namely the topic of random variables, and how we go about computing the expected value of a random variable. As usual, before we start with the new topics, let's warm up by refreshing our memory of stuff that we were looking at before by answering, and we'll do so by answering a couple of questions from our friend Dr. X. The first question is about you. Well, some abstraction of what you stand for. So at RU, we have about 900 bachelor students affiliated with the School of Computer Science. We probably have more, and we'll have even more probably when the fall comes. And they are distributed as follows. That's a rough estimate: 400 in the first year, 300 in the second, 200 in the third year. Now, there is some data having to do with the eating habits of these people. In particular, we're going to focus on vegans. 90 of the first year students, 50 of the second year ones, and 10 of the third year ones are vegan. I'm not a vegan myself, but this is just for the sake of, we could have put anything we want. So, question for you. What is the probability that if you pick a computer science student at random, that student is in the first year or is a vegan? And like the people at home, I'm going to take out our scratchpad paper and note down the important information that we need here in order to try and solve this problem. Okay, so what is it that we have? We have 900 students overall, and we know that 400 are in the first year, 300 are in the second year, and 200 are in the third year. Okay, we also have some information about the incidence of vegans. We have 90 vegans in the first year, then 50 in the second year, and we had 10 in the third year. Okay, so the question was, what is the probability we are asked to find the probability that a CS student is first year or vegan. So how would you answer this question? How would you go about answering this question?
Well, you'd find the individual probabilities and put like a P with a like an F4, like a one or the other.
Okay. So your colleague is saying, yeah, we have a checklist. So let's compute the individual probability of the event a CS student picked at random is a first year, and of the event a a CS student picked at random is vegan. And then in fact, so what we are looking for is the probability of the union of these two events, because we have an OR there. So we are looking at the probability that someone picked at random is either in the set of first year students or in the set of vegans. Or possibly both, yeah. But that's the union, okay, you're in the union of two sets if you're in one or the other, possibly both. It's not an exclusive OR, it's an OR. But good point. Okay, so let's do it. And in fact, I think we do have a formula for computing this. So let's say that F is the event SCS student is in the first year. And V is the event SCS student is vegan. What we want to compute is the probability of the event F union V. And I think we do have a formula for calculating this, which is so it's the probability that the first year student, so that the student is first year, P of F, plus the probability that the first year student is a vegan. But as your colleague is saying, we need to subtract something here, because if a first year student is also a vegan, we counted that person twice in the sum. So we need to remove what? The probability of the intersection, that someone is both a first year student and a vegan. Okay, now we are in business. Why? Well, since I wrote with very large letters to begin with, as it always happens when I'm shrinking the writing pad, let's calculate first the probability that the student is first year. Well, there are 900 students overall. That's the number of students. 400 of them are first year. So what is the probability that the student is a first year student? It's 4/9. So let's plug it in. That's 4/9. Plus, let's scroll up to figure out what the probability that the student is a vegan is. There are 900 students. How many of them are vegan? 150, because it's 90 in the first year, 50 in the second year, 10 in the third year. There are 150 overall. So it's 1/6. Your colleagues here are checking that I'm not screwing up my calculations, my mental calculations, as it's bound to happen sooner or later. So now let's figure out how much double counting we are doing. What is the probability that the student is both in the first year and is a vegan? So let's go up. So there are 90 vegans in the first year. And in fact, sort of one of your colleagues in the second row has already given the answer. So we have 90 out of 900. So it's 1 in 10. Because there are 90 vegans that are also first-year students. So these are the people in the intersection of the two events. Thou shalt be first year and vegan. There are 90 of those who raise their hands and say, here I am. But there are 900 overall, so it's 90 over 900, which is 1 out of 10. Okay, so and now we can calculate. Now I let you do the calculations because you're more likely to get them right. So how do I do this?
You find the smallest number you can, like you can multiply that.
Okay.
You get the whole number if you divide it with any of them.
Fantastic. So now let's put a 90 down here just to make it easy. So we have 40 plus, that's 15, minus 9. So that's 55 minus 9. That's 46 divided by 9. And of course, you can simplify this stuff at your leisure. But the important thing is not the actual calculation here, is the fact, is the process that we follow to get the answer. And in fact, the important thing is this formula here. That's the formula for calculating the union, the probability of the union of two events from the probability of the two individual events and of the intersection of the two events. Any doubt about the process that we followed for solving this exercise? Okay, people are saying, no, there are no doubts. They're not saying anything, but in this case, sort of, I assume that silence means we are fully on the same page. Okay, so what was the other question that we were being asked to address? The second question is the following. Suppose that you know that the student is a vegan. Somebody tells you, okay, I picked a student at random out of the computer science students, and that student is a vegan. Now, what is the probability that that specific student is a first-year student? Okay, how would you calculate this probability? What kind of probability is this? It's a conditional probability. You want to calculate the probability that the student is in the first year, given that conditional to the fact that you know that the student is a vegan. So what we want to calculate is the probability of event F given event V. Okay, and what is the formula for calculating this? The simplest formula that you can use. What is it? Okay, so we want to calculate the probability of the intersection of the two events over the probability of the event that you are given, namely that the student is a vegan. And in fact, we've already calculated all the ingredients here. Okay, the probability of the intersection is 1 over 10. And the probability the student is a vegan is 1 over 6. So this becomes times 6 over 1. So it's 6 out of 10. So it's 3 out of 5. Does this make sense? Okay, so remember that this is actually 1/6. This is equal to 1/6, and this was equal to 1/10. That's something that we calculated before. So you just plugged it in, and you get the result.
But why use this instead of just like, you know that you have 150 vehicles, and you know out of those vehicles, 90 are the first year, so 90.
Okay, so the question is, why couldn't I just use the information that I have about this? Sort of, I know that there are 150 vegans, and I know that 90 are in the first year. Well, you could, in this specific case, you could do this very easily, absolutely. It's just that I wanted to refresh your memory of the formula for conditional probability, so we use that, absolutely. And in fact, you can double check that the conditional probability formula gives you the right result by doing the direct calculation. Well, you've told me a student is a vegan, so I know there are only 150 of those. So my sample space is not 900 strong, but it has shrunk by 1/6. By 6, so it has shrunk to 150. Okay, now I know that 90 out of those are in the first year, so the probability that one of the randomly chosen vegans is a first-year student is 90 over 150, which is 3 over 5, as we just calculated. Okay, very often you can get the same result by using different methods. So if you get the same result by using different methods, then you're a little bit more sure that what you did is correct. If you use different methods for the same problem and they give you different results, well, most likely somewhere you made a mistake. And usually the simplest method that you can apply to solve a specific problem is the one that is typically right, or the one that is more likely to give you, since we are doing probability, that is more likely to give you the right result. So that's, again, the KISS method at work. Keep it simple, and then whatever else you like. Any problem with this? People at home are saying, no, of course not. I can hear them. Well, I can't really, but I sort of hope that they're saying that. Okay, so if there are no problems, and even if there are, I'm afraid we need to continue. But if there are problems with what we've done, scream now. Or forever stay silent, as they say in marriages. In case you ever plan to get married, or you already are. Okay, one of the things we were doing last time round is examining a special but useful type of probability distribution, which is called the binomial distribution. Now, a binomial distribution arises very naturally when we are looking at something that we call Bernoulli trials. Now, what is a Bernoulli trial? Okay, a Bernoulli trial is an experiment where you have two possible outcomes. So the sample space consists of two possible outcomes. And traditionally, the probability of success, these two outcomes are often called success and failure, and we assign the probability P, a probability P to success, and of course, 1 minus P, since there is only another outcome, to failure. Now, in a Bernoulli trial, typically every time you perform the experiment, you ask for a success or a failure, you want these experiments to be mutually independent. What does this mean? That when you perform the second experiment, the result should be independent of the first. When you perform the third experiment, the result, the outcome, should be independent of the first two. In general, when you perform the kth experiment, you should be independent of everything that has happened before. So basically, these are experiments where you don't have any history whatsoever. Every time you do something, it's like the first time. It's a bit like in life. Very often we should remember, but in fact we forget and we make the same mistake over and over again. Perhaps it doesn't happen to you, it does happen to me. Or at least this is what my wife says. And you should believe what she says. She's right. So what is the probability that if you perform n Bernoulli trials, you get exactly k successes? Well, how do we calculate this probability? Well, this is this pk here that you see on the slide. Well, we want k successes, so the probability of getting exactly k successes is p to the power of k. Why? Because it's p times p times p times p, k times. Since all of the trials are independent, we can simply multiply the probabilities. This would not be true if the trials were not independent. Well, all of the other n minus k trials should result in failure. So the probability of getting n minus k failures is the probability of a failure multiplied n minus k times. So this product here, p to the k, 1 minus p to the n minus k, tells you what is the probability of one trial with exactly k successes. To get the probability of getting exactly k successes, we need to multiply that quantity by the number of possible ways in which you can have k successes out of n possible experiments. And that's where this binomial coefficient here comes into the picture. Why? Because what is this? This is something that people call n choose k. That is to say, if you have k successes, you have n boxes where you can place your k successes. How many possible ways are there to do so? And this is exactly what this number here counts. Choose the k boxes out of n. This is where you put the successes. Everything else, everywhere else, you put the failures. And I'm sure you saw a formula for this binomial coefficient. What is this? It's got to do with factorials. So, and there is a fraction line. So what is above the line? N factorial. Okay, and what is below the line? K factorial times n minus k factorial. Okay, that's just a formula that is very useful to remember by heart, unless you want to prove it each time. So this is what people call n choose k, or it's the so-called binomial coefficient. These are called the binomial coefficients. By the way, what's the Icelandic word for binomial coefficient? Well, I look it up on there is an Icelandic English math dictionary where I'm sure there is a word for this. Okay, anyway, n choose k is it's the ways in which you have, it counts the ways in which you have choosing k objects out of n, sorry. Well, if 9 if n is equal to 9. Okay, and the presence of these coefficients is the reason why this distribution that we looked at is called the binomial distribution. So suppose somebody asks you, okay, I give you a coin. Here's my coin. And It has a smiley on one side, that's the head, and it has the tail on the other side. And the probability of getting a head is 3/4, and the probability of getting a tail is 1/4. So it's not an unbiased coin, it's unfair. Okay, so if somebody asks you, suppose I toss this coin 4 times. I toss the coin 4 times. What is the probability of getting exactly 2 heads? The probability of getting exactly 2 heads. Let me write the head here.
Well, you just gave it. Well, we just have the equation.
Absolutely, I just gave you the equation, so that's not a trick question. So all you need to do is to realize that this is a Bernoulli trial. Each time I toss the coin, the coin is unfair, but it doesn't matter. Every time I toss it, the outcome does not depend on what I tossed before, on the outcomes I got before. So every time is like the first time. It's like with kisses. Every time is like the first time. I should say that. I shouldn't say that, I know, but I cannot resist. I need to wake up a few people in the room, so I would try anything which is in good taste, and sometimes if it's not even in good taste, it doesn't matter. Provided it's not overly bad taste, I do it. Okay, so what is the probability that I get 2 heads? Okay, it's 4 choose 2 times 3/4 square, and then 1/4 square. So the probability that if I have a single experiment, I get 2 heads exactly is this thing here. That's the probability of getting 2 heads in 1 experiment. But this thing here counts the number of possible ways. Counts the possible ways. Of getting 2 times a head. And you know, I mean, that's the formula. You can do the calculations. In fact, you don't do them yourself. You feed it to a calculator because it's not complicated, but why should we make mistakes when the machines actually do it right and faster? The important thing is that you realize, okay, I can use this, I can use the binomial distribution to calculate this. Now, let me vary the problem a little bit. Suppose I want to know not what is the probability of getting exactly 2 heads, which is what we just calculated, but I want to know the probability of getting at most 2 heads in 4 tosses. At most 2 heads. So how would you go about calculating the probability of getting at most 2 heads? What is it like? So let me sort of, the probability of getting at most 2 heads. So it's not quite the complement of the probability. Well, it's the complement of the probability of getting exactly 3 and exactly 4. Or in other words, but you can do that, but there is actually a more direct way. Yeah. So there's only one coin here, yeah. Well, or if you toss it 3 times, then what you're suggesting is easier. Your colleague here was suggesting to take it as the complement of another event, which is something you can do. But what does it mean that you want to see at most 2 heads?
1 or 2 or none.
Absolutely. You want to see either 0 or 1 or 2. Or in other words, you don't want to see 3 and you don't want to see 4. So this is actually the probability of getting 0 heads plus the probability of getting 1 head plus the probability of getting 2 heads. Now, why can we just sum the probability of these events? Because maybe before we actually need to take minus something. Because the events are independent, they are totally disjoint. Well, actually, they are disjoint, so there is no intersection. Because if you see exactly 0, well, you haven't seen 1 and you haven't seen 2. If you see exactly 1, you haven't seen 0 and you haven't seen 2, and so on. They are pairwise disjoint. So in this case, the probability of seeing one of them is the sum of the probabilities of the individual events. And okay, we've already seen how to compute this probability. We've already computed it, at least symbolically. And we can use the binomial distribution to compute the probability of seeing 0 heads and the probability of seeing 1. We just used the same formula. So what is the probability of seeing 0 heads? Well, it's the probability of seeing tail all the time, 4 times. So it's 1 over 4 to the power 4.
Which should be 1 in 156. Right.
1 or 2.
64, 256, right? Yeah.
256, absolutely, because it's through to the 8. And the probability of seeing exactly one head is what? Okay, where can you place the head?
First, second, third, or fourth.
Yeah, there are 4 possibilities, 4 places. You can place it in either first, second, third, or fourth. And for each one of these, the probability of getting 1 head is 3/4 times 1 over 4 to the 3rd. Which is, I believe, 3 over 64. Because these things sort of cancel each other out, and then you have 3 over 4 to the 3rd, which is 64. But anyway, the calculations come and go. What stays is the way we go about doing this, solving these exercises. And of course, then we need to sum all these beautiful fractions, but I think this is something that you can do at your leisure. If you really want to know what is the probability of getting at most 2 heads, the important thing is the process of discovery that we went through. Okay, any problem with what we've done? I guess there is a lot of silence at home, and this silence means no, I hope. So, but the natural question that you may ask yourself is, okay, Luca, you told us this is a probability distribution, but why is it a probability distribution? Now, what is the property that every probability distribution should satisfy? So if I give you a function from the sample space, which in this case is the set of numbers from 0 to n, this is the possible number of all successes, the number of successes that you can have. You can have 0 successes, 1 success, 2, or n in the Bernoulli trial, if you repeat the trial n times. Now, to each one of these, we assign a real number whose value is between 0 and 1. But this assignment should be such that if we sum the probability of all of the possible outcomes, what is it that we should get? We should get 1. Now, is it true that if I sum all of these quantities here, letting k range from 0 to n, I actually get 1? It's not God-given, is it? Of course, well, since people call it a binomial distribution, you would somehow make a little bit of an inspired guess and say, yes, somebody has checked that this sums to 1. But why is it? And I'm afraid this may bring back some memories from discrete maths 1, I suspect, where you actually saw these binomial numbers. So suppose I take the sum, or since I've been calling them k, all of these guys here. And let me put sort of a general Q there. In our specific case, Q is going to be 1 minus P, but actually what I'm going to write is independent of what P and Q are. So do you, I think you must have been told what this is equal to. Have you seen this equality? Something which is called a binomial theorem. Well, if you haven't, it really doesn't matter. I'm not going to ask you to prove it. I was just checking whether this had been covered in discrete maths 1 or not. I guess I might have to go and check the course webpage for discrete maths 1 to get an answer. But anyway, so this is a result that tells you how to compute this sum. And it goes under the name of the binomial theorem. And you know, it actually answers the question I asked before. Namely, is actually the binomial distribution a probability distribution? Does the sum of all the probabilities that we assign to the outcomes sum to 1? And you know it does. Why? Because if the sum of all of the probabilities, so this is nothing but the probability of the event k, we're taking the sum of the probability of all of the events Pk, where k can be between 0 and n. And what this theorem tells us is that this sum is equal to this quantity, namely p plus q to the power n. But q is 1 minus p. So p plus q is equal to what? P plus 1 minus p to the power n, which is equal to 1 to the power n, which is equal to 1. That's why what we just defined is a probability distribution. And in fact, the proof of the binomial theorem is not really mind-boggling. If anybody is interested, we could do it later. But I mean, for this moment in time, is is not very important for us. We take it as a black box. It's a library. It's a library code that somebody has given us. And this library code tells us if you see this sum here, it's equal to that. And once we know this, we can immediately figure out why the binomial distribution is a probability distribution. Well, it is, so we can use it without any problem. So let's use it. Let's use it to do something which is perhaps of interest to some of you. So suppose you are designing a communication protocol, and since errors occur in communication, you want this protocol to be able to correct a certain number of errors. Now, life is hard. We would like every bit that we transmit to be received accurately, but there is a probability of error. For instance, the wind might screw up our wireless communication. So we assume that the probability of a successful transmission of a bit is P. And of course, the probability of failure is 1 minus P. And what failure means here is that if you transmit a 1, you get a 0 at the other end, and vice versa. Now, since errors occur, people have been developing for a long time error-correcting codes in computer science. So these codes are such that they allow a certain number of errors to be corrected. So for instance, if you can correct up to 3 errors, if in the transmission of a word consisting of n bits, you make up to 3 errors, it doesn't matter. This word is going to be received correctly at the other end by means of some decoding effort. You know, that's the reason why this error correction or correcting codes are the reason why we can transmit information and receive information from satellites that are somewhere close to Saturn. That's a long way away, and stuff happens over billions and billions of kilometers. But still we can communicate. We receive data from Rosetta, for instance, and this data can be processed. Why? Because there is error correction inside. It's one of the highlights of computer science, in fact, of theoretical computer science. And in fact, the early error correcting codes were based, and some of them still are, on, guess what, linear algebra. Richard Hamming, who was the guy who proposed the first error correcting code, used linear algebra to set up the coding and the decoding. Okay, so let's assume for this example that we have a certain number of errors, E, smaller than the number of the word length, that can be corrected. Now, assuming that the transmission of successive bits is independent, now what is the probability that if I send you, using this error correcting code, an n-bit word, you receive it correctly? Okay, so let's assume that E is 3. If you have 0 errors in the transmission, you receive it correctly. If there is 1 error, you still receive it correctly. Why? Because the code corrects up to 3 errors. If there are 2 errors, exactly 2 errors, you still receive it correctly. 3 errors, you still receive it correctly. 4 or more, no. You cannot trust what you receive. Each time I send you a bit, the probability of successful transmission is always P. The probability of failure is always 1 minus P. And I repeat this trial, sending you a bit, n times. Now, what does this look like? What kind of experiment is this? The transmission of a bit from me to you is a Bernoulli trial. Absolutely. Each time I transmit, the result, success or failure, is independent of what I transmitted before. So you can, since this is a Bernoulli trial, you can calculate the probability that there is zero error using a binomial distribution. The probability that there is one error using a binomial distribution, P of 1. The probability that there are E errors, it's P of E. The probability that there are at most E errors, which is the probability that you actually receive what I sent correctly, is the sum of all of these probabilities. Exactly like we calculated before, at most 2 heads. In this case, it's at most E errors, E failures. So it's a sum of P to the 0, P of 0, P of 1, P of A. That's the probability of successful transmission. So here's a Bernoulli trial, which is probably related to what is happening right now in the Wi-Fi at Reykjavik University, where the probability of success is very, very high because the error correction is, well, the probability of success, there is a lot of error correction anyway. And also we are all within the same 4 walls. Things would be different if we were transmitting to Saturn. The probability of failure would be higher, so you would need better error correction than we need here at Reykjavik University. Okay, so here's a real-life example of a Bernoulli trial and a binomial distribution at work. And on this word of hope, I think it's time for a break.
How much does error correction work?
Let me take this offline.